Okay, so it's 6:10, so I think we can get started now. And sorry for those technical difficulties. The Zoom link is now on the Facebook page, so people might show up while at some point throughout the presentation. But the recording of this lecture will also be posted to the Waterloo Data Science Club's YouTube channel. It's a great resource that if you guys aren't aware of, there's lots of helpful videos on previous lectures. And so, yeah, I'd highly recommend checking it out. And then you can also go there after today if you want to rewatch parts of this lecture or other lectures. Someone in the chat has mentioned that there's an error accessing the notebook. I'm not sure what the issue is. So it seems I'm able to access it. So for the purposes of the presentation, I'll just walk you through it, but when the recording of this is uploaded to the YouTube channel in the time between now and then, I'll try to figure out what the issue is and correct the link so that everyone can access it and read it for themselves. So yeah, I guess I'll get started. So firstly, my name is Jack Douglas. This is the Introduction to Neural Networks and Computer Vision workshop. And basically what I'm going to be doing today is I'm going to be going over the fundamentals of neural networks, the theory and a bit of the math behind it, and so that you can have a greater understanding of how to use them. And then I'm going to go over a couple of applications of neural networks. I'm going to make a simple feed forward, I'm going to show you a simple feed forward neural network and a neural network that classifies images from the Fashion-MNIST dataset. And then at the end of it, I'm going to be looking at some parts of computer vision, specifically the layers that make a convolutional neural network model so that you guys can then make your own CNN models. So let's move on. So yeah, as I mentioned, this is kind of the overview for the workshop. I'm going to start off with a machine learning refresher. For those of you who don't have much machine learning experience, I'm just going to go over the different types of machine learning. And specifically, I'm going to be focusing on supervised learning today. I'm then going to go into the neural network introduction part of the workshop, where I'm going to be talking about what is a neuron, what is a layer, biases and weights, the activation function. I'm going to briefly talk about backpropagation, loss and the loss function and optimizers, and then some other terminology that is useful to know when working with neural networks. Then I'm going to be going over to the notebook that I created for this workshop and kind of going step by step through a simple feed forward neural network that I created from scratch. And then we're going to look at a classification artificial neural network that it uses TensorFlow. For reference, if you guys haven't used TensorFlow before, it's a machine learning library in Python, and it's super popular and super useful. I won't be going into the details about how to use TensorFlow specifically today. There is a presentation that was done in a previous term on using TensorFlow with neural networks. It's already posted to the YouTube channel, so I'd highly recommend you going to check that one out. But yeah, so I'll be using a bit of TensorFlow today. And then, as I mentioned before, I'm going to be going into some convolutional neural networks, and I'm going to be talking about the three main types of layers: the convolutional layer, the pooling layer, the fully connected layer, as well as kernels and filters. I'm not going to be going into too much depth because that's a lot of math, but I'm going to be going over more generally how they are used so that you can kind of so you can go out and explore and look at different notebooks and blog posts and create your own CNNs. So let's begin. So yeah, the machine learning refresher. So as I mentioned, there are three different types of machine learning. There's three different ways, of learning within machine learning. There's supervised learning, unsupervised learning, and reinforcement learning. Today, I'll be mainly focusing on supervised learning, which is basically when you are given labeled data. So when you have a data set which has both the inputs and the outputs. And so the goal of machine learning is to create a function which correlates these inputs with the outputs. The difference with unsupervised learning is that you're just given the inputs, it's unstructured, and you have to come up with a way of structuring that data. And then reinforcement learning is when you want to perform a task and you are rewarded on doing that task well. And that has to do with sort of genetic algorithms, but I won't get into too much detail about those. I'll now just talk about, there's two different types of supervised learning problems, classification problems and regression problems. And so one way that you can distinguish between the two is whether your model is having to predict a class, which is like a category, or whether it's needing to predict a continuous value, like a price, or price is the most common one. So an example of a classification problem is creating a model which distinguishes between a cat and a dog, and you want your model to take a photo of one or the other and be able to determine what it is. And an example of a regression problem is you have a neural network and you train it on a data set of housing data set that has maybe square footage of the house and then the price associated with it, and you want to predict the price of a house based on the square footage. So you're given a data set containing that relationship, and you want to be able to predict on new houses with different square footages. So that's the two different types and kind of the difference between the two. So let's start talking about neural networks. So neural networks, as the name suggests, is created out of neurons, and a neuron is an elementary unit which can receive multiple inputs, and the activation or the output of the neuron is calculated through a formula, which I will talk about in the coming slides. There are three different types of layers within a neural network. There's an input layer, there's a hidden layer, and there's an output layer. As you can see signified in the image on the right, the red, the blue, and the green. The input layer refers to the first layer of the neural network where the inputs are received. So if we're trying to classify an image, for example, like the dog and cat image, the input would be the pixels of the image. The hidden layers in between are the layers in between the input and output layers. So those would be the layers that are trying to extract features and do other sorts of things to help in classifying the image. So like maybe if you have a layer that's extracting the tail of the image, the tail of the animal, to help determine what type of animal it is, if it's a cat or a dog. So it's those sorts of layers. And then the output layer is finally what the actual prediction of the model is. So if the model is trying to predict whether it's a cat or a dog, we have one neuron that's associated with the cat and one neuron that's associated with the dog. And depending on which one is 0 and which one is 1, that helps us to determine what that is essentially what predicts the label for an image. So let's move on. So now we're on to weights and biases. So these are also called the training parameters, and basically they are used to control the strength of a signal of a previous neuron with the neuron that it's connected to, as well as shift the activation function left and right. I'll talk a bit more about what the activation function is in the following slide. But basically, we first take the inputs from the previous layer. So in this example on the right, it's x1, x2, all the way to xm. And we take the linear combination with the weights. So those are w1, w2, all the way to wm. And then we add the bias on top of that. Before I move on, I'll quickly also mention that having an understanding of linear algebra and calculus is helpful, but it's not absolutely essential. You can still understand a lot of the main concepts, I'd say, but it is definitely helpful to have that information. So if machine learning and specifically neural networks is an area that you want to learn more about, I'd highly recommend brushing up on those areas, or maybe learning it for the first time, whether it's from reading blog posts or articles, or even taking like a course on Coursera. So yeah, as I mentioned, weights control the strength between two neurons, and a constant, which is called the bias, is added to the linear combination of the weights and the outputs from the previous neurons. So now onto the activation function. So the activation function refers to the function which determines the output of a neuron. So once we've done the linear combination of the weights and the inputs, and we've added the bias, we then run it through an activation function, and only then do we get the output. We don't. It's important to note that the activation function is this step in between. It doesn't go. We don't just go straight to the output. In this example on the right, we're using the Heaviside function. So if you're taking first year calculus, you might be familiar with it. It's the simplest activation function, but there are many more other more complicated activation functions. And the use of an activation function is to allow neural networks to learn more complicated patterns. It's able to recognize more complicated patterns. So in images, you'll use like usually sigmoid activation functions or other activation functions. I'll actually go over a couple of examples of more common activation functions in the next couple slides. So so this is the kind of the entirety of a single neuron. We take the inputs and then we take the linear combination, which is, and for those of you who haven't taken linear algebra, that's when you multiply a single weight with the single input, with the corresponding input, and then you take the sum of all those together. So it's this sigma summation over here, and then we add b, the constant, and then f represents the activation function that we choose for that layer of neurons. So this is the sigmoid activation function. Its values, as you can see, range from 0 to 1. And it's very commonly used in neural networks because it's useful for converting real number outputs to a probability. So it's commonly used in a lot of hidden layers as well as the input layer. But on this next slide is the softmax activation function, and this activation function is unique to the output layer. It's commonly used in the output layer because, as you can see, we have this vector of scores from the previous layer of neurons. But that's not really helpful, I guess, in determining the confidence of our prediction. So essentially, I don't want to go too far in depth into the math behind this, but basically, we apply the exponential function to the score, and then we normalize it. Normalizing refers to dividing by the sum of all the exponential applications to each of the elements. And what this does is that, similarly to the sigmoid, it converts a score to a normalized probability distribution. So we can see that this second neuron, which corresponds to a particular class, has a 90% accuracy, or has a 90% confidence, not accuracy, and that being the prediction. So usually you'll take like the max of your neuron confidences. But so I'll explain a bit more about that in my demo. So then we're going to talk about losses and optimizers. So this is a really important concept that sometimes gets overlooked when people just use, they sort of plug and play, they look at a notebook and they might want to copy and paste some areas, but this is an important part in understanding how a neural network actually trains and how it learns. So here's a few more definitions. So loss is essentially an indicator of how bad the model's prediction was on a single input. So if you look at these two examples on the right, if the blue line represents the prediction from our model, the loss of an individual sample represents the distance between that point and our blue line. And so we have to come up with different ways of calculating the total loss of our model across all samples, and that's called the loss or the cost function. And as I just mentioned, it's a function which calculates the error in the model across all the samples. And so there's lots of different loss and cost functions. I'm going to be talking about one basic one in a second. And then the goal of an optimizer is to minimize the loss. So that's how we get our model to learn. It's an optimization problem. We want our model to predict as closely to all of the data samples that it was trained on So we want to get the minimum of the total loss across all the entire data set. So yeah, let's go on. So here's an example of a loss function. It's the mean square error. If you've taken statistics, you might be familiar with it. But basically, on the left, we see a bunch of data samples represented by the blue dots, and the red line could represent, it's just an arbitrary sort of line of best fit, but let's say our model wanted to find a correlation between X and Y, and that was what the prediction was. We can calculate the loss for our model by calculating the mean square error for all the different data samples. So here's an equation. There's lots of different ways of calculating loss functions. This was just a tangible example I wanted to give you guys. So yeah, we can move on to the next slide. So now on to gradient descent, which is a very popular optimizer. And it's one that there's many different optimizers, but this is probably the most popular one. And I think it's useful to have some sort of understanding about how it kind of functions. So don't be scared of this. Don't be scared of the equation if you haven't taken multivariable calculus. If you've taken any calculus, you'll know about critical points and the idea of optimizing in that sense. And yeah, I don't want to go into too much detail about the math, but I just want you to be aware that it's all about finding the global minimum within the cost function. So the cost function, a reminder again, is that it is a measure of the error across all the data samples that the model is predicting. And so the goal of the optimizer is to minimize that. And so in the equation, you'll see that there's theta 0 and theta 1. Those are the parameters representing the weights and the biases for the neural network. Now, this is an important concept because that is how the model learns, basically. So it learns by tweaking the weights and the biases that I mentioned about a bunch of slides before. So the strength of each neuron connected to another neuron, the weights, and then the biases being added to an individual neuron. Basically, how a model learns is by tweaking those, by saying, oh, this neuron to neuron connection needs to be stronger, or this neuron to neuron connection needs to be stronger, or this bias needs to be lower, or and so on and so forth. And so it does that by taking kind of, if you look at this image on the top right, this you can see that there's sort of there's a surface, and there's global minimum, or there's at least you want to minimize it as best you can. So where these arrows are pointed in the red represent lower regions, and basically we want our weight and biases, which are theta 1 and theta 0, to basically we want our weight and biases to bring us to these local minimum, and we do that through, or global minima, and we do that through taking the partial derivative, which is again a multivariable concept, so you don't fully need to understand this part, but it's the idea of taking the slope in the direction of the theta 0 and the slope in the direction of theta 1, and you take a small baby step in that direction and you see what happens. So for example, in these two circled areas on the right graph on the surface, you see that if they take it a step to, if they increase theta 0, you'll notice that the circle, that the cost, which is j, sorry, I should have specified that before, j is the cost function, it would actually increase. So that baby step is not good, essentially. So we want to be decreasing every time. We want to be taking these baby steps towards the minimum. And these baby steps are called the learning rate, which is a piece of terminology which brings me to the terminology slide. So yeah, so there's a bunch of other different terms that are useful to know when dealing with neural networks. And so I'm just going to go over them kind of quickly because I don't want to be reading off the slide for too long, but because you guys can refer to this later on. but basically the batch size refers to the number of training samples in one iteration before the training parameters. So that's basically the number of data samples that the neural network will use before it updates the weights and biases. The epoch is the number of cycles through the entire training data set. Fitting and training refers to this entire process, which I've been talking about, which is the tweaking of weights and biases and how the optimizer gets us there and like minimizing that. Overtraining, you might come across that term. That refers to when a model creates a function. When I say function in this situation, I'm talking about like how the model predicts something. But yeah, so overtraining is when when the predictions become too specific to the training data. So like, what does that exactly mean? That means that basically, I'll go back to that dog and cat example. So I've given a neural network a bunch of images of cats and dogs, and I've trained it over and over and over and over and over again to the point where it's quote unquote overtrained. So what that means is that when I give my model a new image, not in the training data set that it's never seen before, it's unable to give an accurate prediction because it's learned too many specific things about the training data. And that's a problem. So like, let's say if a model is completely overtrained, that means that if it sees a new image, it just has no idea what to do with it, which isn't the goal. The goal is for a model to be able to generally enough learn the relation between inputs and outputs so that when you give it a new image, it's able to still predict, even though it's not one that it's already seen, just in the same way that we learn. So actually, that's another important thing that I forgot to mention earlier, which is that neural networks are kind of loosely based on how animals learn, and which is part of the reason why they were given this name, and it's also part of the reason they're structured in this way. It all surrounds the idea that when we were children and we were learning what it meant to be a dog and a cat, our parents probably taught us that, or we learned it from other people. We would be told that, oh, this is a cat, this is a dog. But now as young adults, now that we're older, even if we see a new cat or a new dog that we've never seen before ever, we're still able to tell that is a cat and a dog. So that is kind of like our model is trying to replicate that same idea, extrapolate what our pattern recognition is to new cases. So yeah, that's what overtraining is. It's when a model isn't able to predict on new images and do that effectively. And so the reverse of that is undertraining. So that's when the model is too general. So an example of that is if the model, whenever it sees, for an example, let's say the model had let's say the training data was 3/4 of it, or no, even more. Let's say 90% of the images in the training data were dogs and 10% of them were cats. That represents a common issue with that plagues data scientists and machine learning engineers. But what your model might do is that it might just classify them all as dogs if the training data set was 90% dogs and 10% cats. And the reason it might just classify them all as dogs is because if it does that, it gets 90% accuracy, right? Because 90% of them were dogs and 10% of them were cats. So if it predicts them all being dogs, then it will get 90%. That's obviously a problem because that means that it doesn't really know the difference between a cat and a dog. It's just saying that everything is a dog. And so that's sort of an example of undertraining where the model's pattern recognition is too general and it doesn't actually have an understanding of what the difference is. And so that means that typically how you solve that issue is by adding more epochs. So you want to run through the data more. And it's also solved by helping to balance your data set. So if you have an imbalanced data set, like the one that I was just talking about, where you have 90% dogs and 10% cats, you may want to try to find more cat images to help train your model so that it doesn't think that 90% is really good when it's just classifying everything as dogs. So yeah, learning rate. So that's, as I mentioned before, when I was talking about gradient descent, those are the baby steps. It is a hyperparameter, which says how much the weights and bias are updated during training when it's trying to minimize the cost. Class, it means a category or a label. And backpropagation, basically this in itself could be kind of like a part, like at least half of a presentation, so I didn't want to spend too much time on it. It's essentially it's quite a bit of complicated math, but what it does is that it calculates the gradient, which is needed in the gradient descent optimizer. This delta over delta theta j, that is the gradient. It basically calculates that efficiently, and so that was a huge breakthrough that was discovered within the past how many years? It was discovered relatively recently by Dr. Hinton. He's a professor at U of T, a brilliant guy. He's nicknamed Godfather of AI. So if you want to learn more about backpropagation, you might want to search him up. But a generalization of what it does is that it calculates the gradient efficiently so that we're able to use gradient descent as an optimizer. So yeah, onto some neural network architectures. So there's lots of them. There's tons of them, but within the images that I'm showing you on the screen, there's some general groupings of neural networks. There's perceptrons, which is this one in the top left. It's the simplest neural network. It is a binary classifier where you give the neural network a vector of information, and it tells you if it's part of a class or not. So that can be, so yeah, it's a binary classifier. It's the simplest neural network. Another type of neural network is convolutional neural networks, which I'll be talking about later. Those are commonly used for computer vision problems, which I'll also talk about more in detail. But you can see that in the top, the circles that are colored pink, those are convolutional networks. There's also recurrent neural networks. Those are networks with blue circles, and also there's long and short-term memory neural networks. But there's a whole bunch. But yeah, you could do a lecture on each of these. You could do multiple lectures on just each of these. But yeah, just so that you're aware, there's tons of different architectures, even more than the ones listed here. So you can create your own one. These are just sort of what generally the shape of neural networks can look like and what they are categorized. So yeah, now on to the applications portion of this workshop. So I'm just going to be showing two applications. The first being a simple feed-forward neural network created from scratch. And then I'm going to be looking at using an artificial neural network, not a convolutional one, just an artificial neural network to classify images in the Fashion-MNIST dataset. So we'll start with the first application. So right here, you can see I'm just importing the NumPy library, which is a library that can manipulate arrays and vectors, and it is much faster than traditional Python lists. So this is a very popular Python library that data scientists use, and so I'd highly recommend, if you haven't already, become more familiar with it. So our activation function for this neural network that we'll be creating is the sigmoid. So just going back really quickly, you can see that the sigmoid is 1 over 1 plus e to the negative z, where z is our output. So yeah, we've done that exactly. Our neuron class is here. We are initializing the weights and biases of the inputs to that neuron, as well as we're defining what it means to feed forward, which is exactly the calculations I was talking about earlier, where we do the linear combination of the weights and inputs and then add the bias after. So you can see that in the equation there. This is also called the dot product. Yeah. So yeah, the dot product of the two vectors, the inputs and the weights. and then we're returning the activation function of this output. So remember, the activation function goes in between the linear combination and the actual output of the neuron. So we'll just do a really simple example. We're going to look at a single neuron, and the weights of the inputs to this neuron are going to be 0 and 1, and the bias of the neuron is 4. So we are creating a neuron object called N, and so basically if we're using the inputs to be 2 and 3, we can calculate that the output of this particular neuron. So if you look at the image that I've put in the notebook, you can see that we're doing the weights vector. It's important that's not multiplying, that's dotting it with the inputs vector x, and then we're adding the bias after. So we're doing weight 1 times input 1 plus weight 2 times input 2, and then all of that we're adding 4 to it, and the result is 7. But the output of this neuron is the sigmoid of 7. So we do f of 7, and that ends up being 0.99. So just for confirmation's sake, we're creating an input vector of 2 and 3, and then when we put x into our neuron, we can see that the feed forward, the result is 0.99 as expected. So yeah, this is kind of was entirely done from scratch in TensorFlow. A lot of this math is done for you, and all this object creation is done for you. And so, or not object creation, but creating the class is all done for you and whatnot. But you'll find that as you do more and more machine learning, that it's really useful to have involved knowledge of how to create it, especially because there are some limitations to TensorFlow. And so there's only so much you can do without having a fundamental understanding of neural networks. So here's our neural network class. It's our first neural network. So I just showed a single output for a single neuron, but here's our first neural network. It's a feed forward neural network. It's fairly simple. The input layer, there are 2 input neurons, and then in our hidden layer there are 2 neurons as well, and then our output layer has just a single neuron. I'm declaring the weights and biases for for the hidden layer and the output layer to be the weights to be 0 and 1, and the bias to be 0. I've done all that, put all that information into the first neural network class. You'll notice that in my class for the first neural network, I'm using the object neuron. So and yeah, I'm using the object neuron, and I've redefined what the feed forward is for this neural network. Oh, and for some reason, okay, my calculations aren't. I wonder if I refresh, is that my calculations should be. Okay, my calculations aren't showing for some reason. I'm not sure why that is. There should be an image there showing the calculations. So if you go to the YouTube video when this is uploaded and look at this notebook again, you'll see it with the calculations posted. But essentially, if you do all these calculations, like x1 times its weight going to the H2 neuron, all those calculations, you'll see that the output is 0.72 as expected. That's too bad that we don't have the calculations, but essentially it's the same thing as the single neuron, and you just apply it to each of the hidden layer neurons and then also the output layer neuron. And you'll see if you do that by hand, you'll see that the output is 0.7216 and so on as expected. So yeah, this is the first neural network. Maybe many of you have ever created from scratch. If you want to play around with it, you're welcome to do so. You can make it more complicated, add more hidden layer neurons, add more hidden layers. You can do that as well. You can add more input layers and so on. But this is how you would create a neural network from scratch. It's not too complicated. This is just a feed-forward neural network, though. It's much more difficult to create a convolutional neural network, and it's also it's somewhat difficult to create. It's fairly difficult to create convolutional neural networks. You'll need to have a very strong understanding of the math involved, but it is doable, obviously. So yeah, I thought this would be cool to kind of show from scratch how to create it, as opposed to using TensorFlow, which most people are used to. But I will go into a TensorFlow, an artificial neural network using TensorFlow. I'll show you another example because now I'm going to be starting to talk more about computer vision. I thought this would be like a cool intro project maybe for some of you, especially those of you that are wanting to work on computer vision projects. If you go on Kaggle, you might have seen Kaggle. For those of you who don't know, it's a data science contest websites. So there's lots of competitions there. So I'd highly recommend, if you're interested in data science and machine learning, to go check out Kaggle. Kaggle spelled Kaggle. But if you have been there before, you might have noticed a digit recognition competition. And so those images come from the MNIST dataset. Today we're going to be using the Fashion-MNIST dataset, which is basically a dataset containing images of clothing. And the goal of this neural network that I'm going to be creating in this notebook is to predict the class of an arbitrary image. So yeah, right here we're first importing all the TensorFlow libraries that we need, and then I'm loading the Fashion-MNIST dataset into the NumPy arrays. Note that load data doesn't work for all datasets. It does work for the Fashion-MNIST dataset because this is sort of like a default dataset that TensorFlow has, and it's already pre-specified that the training image, there are 60,000 training images and 10,000 testing images. So in many cases, you might have to use a data frame and do this manually, which is a data frame. The library that people use for data frames is Pandas. So that's also something you guys might want to become more familiar with. But I'm just, for time's sake, I'm just sort of using the functionality that TensorFlow offers for the Fashion-MNIST dataset. So as you can see, I'm also printing the type of each of these, and they're all NumPy arrays as expected. So here are the labels for the data set. There's t-shirts, trousers, pullovers, dresses, coats, sandals, shirts, sneakers, bags, and boots. Note that these aren't the labels that I came up with. These are the labels that the people that created the data set came up with. Oh yeah, okay. That's strange. Okay, also this is supposed to be showing, plotting some examples, but for some reason, this notebook is appearing to be kind of funky. Yeah, I apologize about this. I'd say this script right here prints or shows, some examples of the data set. Maybe I can just quickly search up an example. So yeah, these are some examples. I don't know why that script wasn't running. I'll have to figure out all these bugs before we upload it to YouTube. But these are what the images from the dataset look like. So you can see there's pullover, trousers, bags, boots, t-shirts / tops, pullovers, a coat. And we're basically trying to predict, given a new image, we're trying to come up with a model that can predict the class of a new image, having never seen it. So going back to the notebook. So the first thing that we have to do is we have to normalize the image. So what does that mean? So I'll first note that all the images in the Fashion-MNIST dataset are grayscale, which means that the pixel intensities vary from 0 to 255 and everything in between, where 0 is black, 255 is white, and everything in between is varying shades of gray. So here's the result from printing the pixel intensities of a single image in the training data set. So as you can see, there's zeros and there's ones and there's some 255s here and there. Basically, those correspond to whether, yeah, as I mentioned before, whether it's black or white in the image. Basically, how also this looks is that this first list that I'm highlighting here within the matrix corresponds to the first row of pixels, and this row corresponds to the second row of pixels, and so on and so forth. And these images are 28 pixels by 28. So if you count up all the elements in this array, there should be 28 of them, and there should be 28 lists within this list of lists. So yeah. So normalizing refers to changing the dividing all the pixel intensities by 255. Or sorry, it refers to dividing by the total number or the highest number within the image, basically, so that all of the values are between 0 and 1. And so to do this, we first have to change the type of the images from integers to float, so that we can actually do that division and so that we can have decimals as opposed to just zeros and ones. Because if you guys are familiar with Python, integer division, if you do, for example, 1 divided by 255, that's just going to be 0, which isn't what we want. We want a decimal. And the reason we normalize is to make calculating the gradient easier. And so it also makes training the model incredibly much quicker, so that the optimizer can converge to a local minima much faster. So yeah, the next thing we do is we reshape the data. We flatten the images from 2 dimensions to 1 dimension. So as I mentioned before, the images in the Fashion-MNIST dataset are 28 by 28 pixels. So we basically reshape the image so that it's 1 dimensional. So what does that mean? We essentially take each row of pixels in the image, and we just basically we append them to one long list of pixels. So if there's 28 pixels in the first row, 28 pixels in the second row, all the way down to the 28th row, that means there are 784 pixels in total in every image. 784 is just 28 times 28. So we basically want to reshape it so that's 1 dimensional, so that our particular neural network can each neuron in the input layer will correspond to a pixel intensity. And so I'll talk a bit more about that when I get to creating the neural network. The next thing is the one-hot encoding. So again, this isn't super duper important, but I'll just quickly touch on it. So we're using 2 categorical. So what does that do? If any of you are familiar with one-hot encoding, it's basically what this image right here is doing. You can see that in this diagram, the word red corresponds with the ID 0. The word sticky, or the class sticky, I mean, corresponds with the ID 1. The class clay corresponds with the ID 2. This is just like a general example I saw on the internet. When you one-hot encode it, you basically turn it into each class into a vector, or a vector corresponds with each class, where the top, where red corresponds to the top of the vector being 1 followed by 2 zeros. Sticky the sticky class corresponds to 0 followed by a 1 followed by a 0, and then the clay class corresponds to a vector that is 0 followed by a 0 followed by a 1. So that's essentially what we're doing, and the reason we're doing that is because these one-hot encoded vectors, they correspond to the outputs of the output layer. So the neuron, which corresponds with the red class in this example, should be 1 if that's the prediction of the model, or the second neuron in the output layer should have an output of 1 to indicate that it corresponds with the sticky class, and so on and so forth. For our example, though, we have 10 labels. So essentially, it's like doing this example, but with 10 rows and 10 columns. So it's like a 1 followed by 0, 0, 0, and so on and so forth for each class. So now we build the model. So we import Keras, which also I'll mention this as well. It's an interface that is like used in tandem with TensorFlow. It's an interface for creating neural networks. So becoming familiar with Keras is also something I'd recommend. So this neural network that I'm making is very simple. Basically, I'm using a sequential neural network, which is just the same thing as it's just an artificial neural network. Basically, that was the name that they came up with for the ANN class. So you'll see that I add one layer and I use the activation function of a sigmoid. That's the activation function I've been talking about. And I add 784 neurons. So each one of these neurons corresponds to a pixel intensity within the image. I then add another hidden layer, which is has 30 neurons in it, and also use the activation sigmoid. I add that so that basically the model can recognize more complex patterns. If I didn't have that layer, the accuracy of the model wouldn't be as strong. There wouldn't be as much. There wouldn't be as many possible weights and biases that could be changed and manipulated to correspond to the correct pattern recognition. And then the last layer I add is the output layer. There's 10 neurons, and each neuron corresponds to a particular class or label. Class and label are interchangeable. They're like synonyms. And I use the softmax activation, as I was mentioning in the presentation earlier. Here is a quick summary of what our model kind of looks like. Again, so we have the first dense layer, 784 neurons. Then we have this hidden layer with 30 neurons. And then we have an output layer that has 10 neurons. And so the next step is we compile it. So compiling the model basically means we're specifying the loss function or the cost function that we want to use. We're specifying the optimizer that we want to use, and we're specifying the metrics as well. For this case, I'm using accuracy. SGD stands for stochastic gradient descent. So that was the optimizer that I referenced in the presentation. And the loss function that I'm using is the categorical cross entropy. So this is a loss function that is used for it's a loss function that is used for many classification problems. I didn't want to talk about the math there because it's more complicated, and so I thought it might confuse people. But essentially, it's a loss function that uses some kind of complex math to be able to determine the error in a classification model. So then the final step is to train it. So basically running the training data through it and seeing how it compares to the labels of the predictions to see how accurate it is. I set the batch size to 50 and the epochs to 10. And you'll see right here that TensorFlow, this is like TensorFlow's output for a model that's training. You can see that by the end of 10 epochs, the accuracy is on the training data is 77%, which isn't very good, to be honest. But how we would improve that is by likely adding more layers to the network and by increasing the number of epochs so that the model can train more times and learn the data better. So basically what this, that's where we're at. And then the last step is to evaluate. So you might be wondering why I've already calculated the accuracy as 77% on the data set. Why do I have to recalculate it or reevaluate it? Well, this goes back to the idea of overtraining and undertraining and just training in general, which I talked about on the terminology slide. Basically, the worry about just relying on this accuracy is that it can be deceiving. So it could if my model was overtraining, this accuracy would be 100%, or it would be 1.00, right? Or 000 and so on. And if I didn't have testing images or other images to evaluate the model, I might think, oh, my model is fantastic. It has a perfect accuracy. Well, that's not actually the case. As I mentioned before, that would just mean that it overtrained, and so it knows every single one of the training images that I showed it, but that doesn't necessarily mean if I showed it a new image, it would perform as accurately. So that's why we set aside some testing images to actually test our model. These are images that the model has never seen before. You want to have a decent number of testing images so that it represents a pretty accurate measure of how accurate your model is. And so there's 10,000 testing images in this data set with labels. And so right here, I calculate the accuracy. So the actual accuracy of the model is 76%, which in this case was pretty close to the accuracy based on the training data. But in some cases, as I mentioned, if it's overtraining, your training data accuracy might be like 99% or something, or super high, even higher than that, like 99.999% accurate. But then when you evaluate the model on testing images, you might have a 60% accuracy or even lower, like much, much lower actually. So yeah, those are the two examples. The two applications that I've done, I did one from scratch, and then I did a kind of a simple computer vision application just using an artificial neural network. I'll make sure that when this video is uploaded, I'll have made sure that this notebook is one, accessible, and two, it shows like all the images that it's supposed to. So yeah, now I'll move on to specifically convolutional neural networks. So this is the computer vision part. I'm not going to spend too long on it because I know we have about 10 minutes left. So I'm going to basically explain what they do. I'm not going to go into the math. I'm going to do some math, but not like the same level of math that I did with the previous equations that I brought up. But I'm just going to be talking about how you guys can dip your feet into creating convolutional neural networks, what convolutional neural networks are, like why they're used, and how it relates to computer vision, essentially. So CNNs are used in computer vision because they're very good at extracting features. And by features, I mean characteristics within an image. So going back to this, or let's think of a better example. Let's actually use the Fashion-MNIST dataset as our example for this part of the presentation. So let's say we have a convolutional neural network, and it's trying to do exactly the same problem that we were trying to do. It's trying to classify images from the Fashion-MNIST dataset. And what CNNs are really good at are extracting features. So a feature in one of those images might be, does it have, if it's trying to determine between a t-shirt and a sweater, right? Or sorry, like a dress, convolutional neural networks are really good at being able to say, oh, that is a sleeve. Dresses, or sorry, that is like a long sleeve. Dresses have long sleeves, therefore it's a dress, as opposed to, oh, that's like a short sleeve, therefore it's a t-shirt. In a very big generalization, CNNs are basically good at picking up those things within images. They're able to extract high and low level features. High and low level features meaning things as abstract as like just a lines or an object, edge detection. Like a CNN can extract the edges of an image, and it can extract like higher level objects like, oh, that is an entire t-shirt, exactly, or that is an entire, the difference between a sandal and a boot. It's able to determine, like, since those are kind of two close classes, it's able to determine between the two. So now I'm going to talk about the kind of building blocks of CNNs. So there's kernels and filters. Those are basically what actually extract these features. So I'm going to first talk about those. And then there's three different types of layers. There's the convolutional layer, there's the pooling layer, and there's the fully convolutional layer. So yeah, I'll get along. So here are some more definitions. I know there's probably all tired of all the definitions I've been showing, but I'd say that you don't have to remember all of them at this very moment. I'd say as you do more machine learning and use neural networks more, you'll just sort of start to know what these terms mean. But I think that the definitions are kind of useful they're definitely useful for telling you about what they are and what they do. I'll also show some images, but basically, I'm just going to go through all 4 of these definitions on the screen. A kernel is a matrix which is applied to an image to extract features. A filter are kernels that are stacked together. They're applied simultaneously to an image. Convolve, that's a verb. It means the process of a kernel being applied across an entire image. So that's a term you might see. And then stride. Stride refers to the number of pixels that the kernel moves before being applied again. So here's an image just to kind of demonstrate these 4 definitions that I've given you. So suppose this input on the left is some sort of, let's say it's some image, some normalized image. So this, if it's a normalized grayscale image, that means that zeros are black and white is, and sorry, 1 is white because 255, it's been normalized. So 255 by 255 is 1. So 1 now corresponds to white. Anyways, so yeah, the left is an image representing pixel intensities. In the center here, this like kind of purple 3x3 matrix is the kernel. So the kernel, we dot it with another 3x3 image patch from the original input image, and the output is then we get the output from dotting those 2, and then we send that into an output image. So you'll notice that this 31, you can calculate that by, if you dotted this image patch with the kernel. Dotting, again, for those of you that haven't taken linear algebra, is basically when you multiply the corresponding places within the matrix and then you sum them all together. So it would be 1 times 1 plus 1 times 3 plus 1 times 5 plus 1 times 6 plus 1 times 7 plus 1 times 9. If you just took the sum of what I just said, you'd find that that is equal to 31. And the place where you put that corresponds to the origin or the center of the kernel. So if you compare the sizes of the input and the output, you'll notice that the output is a 4x4, whereas the input was a 6x6. And so the reason for that is because you basically scan this kernel across the entire image. And each time, each different image patch that you dot it with produces a different output, and that goes into the output. So in the top layer, you might see that there's only 4 places that this kernel can move across, and then there's only 4 positions upwards and downwards that the kernel can move. So that's why the output is a 4x4. Is 4x4. Also note that the stride in this example is 1. The stride could be, it doesn't have to be 1. It could be 2. It could be 3. It could be any integer. The stride, again, just a reminder, meaning the displacement, how much you displace the kernel before you apply it. So in this case, you're just shifting the kernel 1 pixel over, and then you one pixel over, and then you do it again, 1 pixel over, 1 pixel over, and so on. And same downwards too. You just apply it downwards, 1 pixel, downwards, 1 pixel, and so on. So yeah, this is kernels and filters. And then also it's important to mention the reason that it has filter in brackets is because in this case, we're just applying 1 kernel. And so if you're only applying 1 kernel, then the filter is the kernel. The filter, a reminder, is the collection of kernels. So sometimes you might apply multiple kernels simultaneously to an image. And so in that case, the filter isn't the kernel. The filter is obviously all of the kernels together. But yeah, so okay, actually one last thing is that, so this is really important to focus on, that this is the area where things like edge detection and other sorts of feature extraction is done. The kernel is what's able to extract all this information from the image. So having an understanding of how this works is useful in terms of when you're creating your own neural network, CNNs. I mean, when you're creating the kernels, you might want different size kernels. You might want to search up kernels that extract particular features from images. So just understanding how this area works can be helpful, especially for creating specific CNNs for specific problems. So if you want like the edges, then you might want to search up what is the kernel for edge detection. There's going to be many, but you can choose a couple of them or several of them. And so that is, I thought that would be important to know. So on to the types of CNN layers. So as I mentioned before, there are 3 different types. There's the convolutional layer, there's the pooling layer, and there's the fully connected layer. So here's some more definitions. So the convolutional layer, as you might have guessed by now, is the layer where the kernel/filter is applied or convolved across the image. So that is the layer where the filter, is dotted with all the sections of the image. And then that layer is where you extract features from the image, edges of an object, higher level features such as like particular shapes, and so on. The pooling layer is a layer which reduces the spatial size of the image, and it helps to lower the parameters. So you can kind of think of it as almost blurring in a way the image. So you can think of it as globbing together areas of the image that are similar. I'll talk about specific types of pooling, specific type of pooling layer that is commonly used in a second. And then the last type of layer is the fully connected layer. So the fully connected layer is a layer in which all the neurons are connected to every neuron in the following layer. You might notice that the 2 networks that we did in our application, and the applications I went over, are also fully connected layers. So outside of CNNs, or at least in many artificial neural networks, all of them are, not all of the layers, but like many of the layers are fully connected layers. So this is a layer that's common to several different architectures of layers, whereas the convolutional layer is specific to the CNN. So yeah, that's the difference. And so the fully connected layer takes the features that are extracted and it pieces them together. So it says like, oh, this is a dog ear. Oh, this is a dog nose. This is a dog tail. These are all features that were extracted from the images. It then uses that information. The fully connected layer uses that information to say, oh, this is a dog. So yeah, so now I'm going to just show some images of each of these. So this is a convolutional layer, kind of how it works. Kind of what I was showing with the kernel slide, how the filter goes across the image, it maps it onto an output, and the size of it is smaller. Yeah, and it scans across the entire image, as I mentioned. So I kind of went over this, so I'm going to go on to the next slide. So here's the pooling layer. This is specifically a max pooling layer. As you'll notice, filter and stride is used again, but in this context, it's used for taking the maximum number from the filter. So what does this mean? So basically, we look at the top 4, we look at groupings of 4 elements within the input, and we take the maximum of it. And so the stride says to move over to 2 pixels. So then we look at the maximum of the green section. The stride also says to move downwards 2 pixels. So then we take the maximum of the yellow section, and then so on, we take the maximum of the red section. So the result of the pooling layer from this input would be 9786. We're taking the maximum of the filter size on that input image, and the stride is 2 by 2, and the output is the maximum of each of those sections. And what that does is that it basically simplifies the image so that computations are easier. It makes the image more general. So you don't want too many pooling layers, but it makes converging, it makes training the model quicker. It also improves accuracy to an extent. A way you can think of it is also as if you had an image, just like our grayscale images, in sections that were similarly colored. You just all condense that into 1 pixel. All areas that were are similarly colored, you condense them all into just a singular pixel. And so what that does is it will make the image more blurry, but it will make it will make the pattern recognition part of the model much more accurate. Well, not always, but I mean, used in the right way, it will improve the accuracy of your model. And then so the last layer, the last type of layer is the fully connected layer. You've seen, we've been using that for a lot of the first part of the presentation. I talked a lot about that. But yeah, so essentially it's each neuron is connected to the, each neuron in the fully connected layer is connected to all the neurons in the next layer. So you can see in this example, the feature extraction goes into the fully connected layer. And then that layer, each of its neurons are connected to the output layers. And in this particular example, I imagine this diagram is used for classifying types of cancer. So the two outputs would be benign or malignant. So based on the feature extraction, the fully connected layer pieces together all the features that have been extracted to determine whether that corresponds to a benign cancer or malignant cancer in the image. And so, yeah, that's basically the last type of CNN layer. I'll say in terms of the order of them, the fully connected layer usually goes near the end of the CNN, and the convolutional layers and the pooling layers usually go from like the very beginning in the middle, all in the hidden layers. There you use like a combination of a convolutional layer, and then maybe you might want to use a pooling layer, and then you use another convolutional layer basically to keep extracting from this like more blurred image. And then maybe you want to use another pooling layer to make it like even quote unquote blurrier, and so on and so forth. But then just right near the end is where you want to use the fully connected layers. You can have more than one, you can have like one or two, but those come right before the outputs, and those take all the features extracted, as I mentioned, and determines whether it's been like whether it's one class or another or another or so on. So yeah, that's kind of the architecture of a convolutional neural network. So now that you understand kind of the building blocks of that, I'd recommend it would be much harder to create a convolutional neural network from scratch than it is to create just a feed-forward network. So I'd recommend, if this is an area you want to learn more about and do more, specifically computer vision is what I'm referring to, I'd recommend you use TensorFlow or maybe OpenCV, and you look at documentation for those libraries and start playing around. I'd highly recommend you go to Kaggle and look at some notebooks or read blogs. Just search up like a CNN with TensorFlow articles or blogs or notebooks, and just learn the documentation. But now hopefully you have an understanding of what to do actually. Once you know how to use TensorFlow, how to actually create your very own neural network. And so whether you want to use one fully connected layer or two, or have multiple convolutional layers or multiple pooling layers, hopefully now you have a kind of general idea about the purpose, the use of each, and where each is used, and how you might want to use it for your particular problem. So that is the end of the workshop. I'm happy to answer any questions now. Okay, yeah, I see that someone, okay, whoops, they asked a while ago. Alexi, can a single neural network be used for both classification and regression, or do you need separate neural networks for each problem? That's a good question. I believe, I've never heard of a neural network. I've never seen a neural network that can do both a regression and a classification problem. I don't want to say definitely there isn't, because like it's possible, but I'd be kind of surprised if it could do both, because the thing about classification problems is that there's sort of a limit to the number of classes typically. There's usually a limit to the number of classes. Whereas with a regression problem, it's continuous. That's sort of the distinguishing feature kind of between classification and regression. Classification, there's only a set number of classes or labels, whereas regression, it can be like an infinite number, right? If going back to that example I used at the very beginning of the presentation with housing, if I want to predict the price of a house based on square footage, there could be an infinite number of possible prices, all of which are dependent on the square footage, if that makes sense. So I would imagine you'd have to separate the neural networks for each problem. But that's a good question. It'd be cool if there was one that does both, but I don't think there is. So someone else has asked a question. So the convolutional layers first splits the data into, they ask, the convolutional layers first splits the data into specific groups of features. Then the pooling layer processes each extracted feature from the convolutional layers and filters out features based on the kernel. Then data generated by this layer is then processed in the fully. And since the amount of features are reduced as only the important features are focused on. Yes, that is a great explanation. Yeah, that's a fantastic. So just to reiterate what Redwan, I think that's how you pronounce his name. Sorry if I pronounced it incorrectly. He's asking about the architecture of the convolutional neural networks. Essentially, the convolutional layers are used first. Like that's usually the first hidden layer, and that is to extract features. But as you mentioned, sometimes some features are obviously more important than others. Sometimes you'll have noise in an image, and that you don't want to be focusing on the noise. You want to be focusing on the key features within images. And so you use the pooling layer to extract these features and make the image less complex. But at the same time, that's also highlighting which features are important and which ones are less important. And then you might want to use another convolutional layer based on that, on this reduced complex image. And then you might want to go back and forth between convolutional and pooling. And at the very end, as you mentioned, you have the fully connected layer to kind of piece together what features are in the image and what that corresponds to in terms of the class for whatever you're trying to predict. So yeah, great, good question. And yeah, good. You kind of explained it in a way in your question. That was good. So Lexi asks, how do you select the number of layers in a neural network? Is there like a formula to follow? How do you know what number of layers is best for your problem? That's a good question. So yeah, I guess, yeah, for your CNN, yeah, okay. There isn't, I don't believe there's a formula, at least there's not one that I'm aware of. So the short answer is no, there isn't like a specific number of layers. I'd say how you would find out the number of layers you might need is, this might not be the response you were looking, at least, actually, I shouldn't say like there definitely isn't a formula, because there could be a formula, but to the extent of my knowledge, it's, if you're creating a neural network from, if you're like just creating a neural network, it's somewhat trial and error in the sense that depending on how well your model fits the training data and how well it performs on testing data, that might affect whether you want to add more layers to the neural network. So for example, if you have a convolutional neural network that's classifying images and your accuracy isn't very high, you might want to add more convolutional layers, or you might want to remove pooling layers, something like that, and see how that affects the accuracy. Because if your accuracy isn't very high, that might suggest that you're underfitting. So you're not finding enough of the features that represent what it means to be one class versus another. So it's a little bit of trial and error. If you're creating it from scratch. There's another thing that you can do actually though, which I didn't actually talk about because I didn't talk about it because it doesn't really use any of the concepts I've talked about, I guess. But you can use pre-trained networks. So what is a pre-trained network? Basically, there was a competition created, I think in 2014, I think around then. I can't exactly remember. It was called ImageNet. It was the ImageNet competition. And basically a bunch of really smart data scientists and machine learning engineers created these models, all of them being, I think, like CNNs mainly, because as I mentioned, those are like, that's the network for computer vision. They created these models to compete in ImageNet, in the ImageNet competition. So what was ImageNet? ImageNet was basically, it was like the biggest, it had the most different classes of any competition, and it challenged people to be able to label all of them. So it had everything from very specific like breeds of animals to like everyday objects like a car or a plane. It would have like specific breeds of horses, birds, butterflies, etc., like everything. And so it was a super huge, large scale classification competition. And basically, as I said, a bunch of people came up with particular CNN architectures that performed very well on ImageNet. And since then, there's been a concept that has been found out, and it's called transfer learning. So this in itself is, I could go on and talk about, but basically transfer learning is the idea that a model learning to classify, a model can learn to solve one problem, like classify particular classes for one thing, so like cats versus dogs, and you can actually, with transfer learning, you can actually reapply this model to a completely different problem. You save the weights that were determined by training on the cats and dogs images, and then you can actually apply that to another problem, like determining between horses and zebras, right? So the idea of transfer learning would involve me to go into more depth that I don't really have the time to go into, but I'd recommend, if this is if you guys are working on computer vision projects, you might want to look into transfer learning and pre-trained CNN models. There's lots of them. Like, I'll give you some examples. There's ResNet 50, ResNet 101. There's VGG16. There's what else? Exception. There's tons of them. And basically, all of these models were trained on ImageNet, and you can use transfer learning to apply it to a specific problem that you're trying to work on. So if you're working on a cancer classification problem, you want to determine between malignant and benign cancer images, you can actually use VGG16 or ResNet or one of these models, which are already trained on the ImageNet images. And then using transfer learning, you can just change sort of the last like 4 or 5 layers in your new model and keep the weights and biases that model learned while training on ImageNet. And that's like a really powerful concept that has made classifying, because ImageNet was so expansive and the weights and biases were so, you can kind of think of them as being so finely tuned to almost all classification problems, you're able to just keep those weights and biases constant from when it trained on from ImageNet and apply it to a completely new problem, which is really cool. So yeah, I'd recommend checking out transfer learning, pre-trained models, and CNNs. I say this though, I think everything that I've mentioned in this presentation is important. And so I think having a foundational understanding of neural networks and convolutional neural networks is very important. If you use transfer learning, you probably won't be using a lot of the concepts that I've been mentioning already, but I still think it's really important to know this, because there's only so much that you can, when you enter when you go on a co-op maybe where you're having to do computer vision, or like in the workforce, there's only so much you can do with TensorFlow even, and transfer learning and things like that, where you might have to start from scratch, not using any of this, doing what the very first application, doing a lot of it from scratch. And if you're not able to do that, if you've been doing a lot of kind of plugging and chugging and don't have a foundational understanding of how neural networks work, then there's obviously going to be a bit of an issue. So, yeah, I think that is it. Does anyone have any other questions? But also, I should mention, if you have questions, feel free to reach me on Facebook, or you can email me. My email is jack.douglas@uwaterloo.ca. This video will be posted to YouTube. So if you want to come back and watch it again, or watch different parts of it, or look at the notebook or the presentation and just like look at some of the definitions, that will be all posted to the YouTube channel. So yeah, if no one has any other questions, I think that's everything. And as I mentioned, you can send questions to me after. But yeah, I think that's everything. So thank you very much for coming. Thanks for listening. And I hope you guys check out some more videos on the YouTube channel and keep coming to other workshops done by the Data Science Club. So again, thank you everyone, and have a good night.